When we think about black holes, we imagine an entity of infinite density, a singularity, with gravity so strong that even light cannot escape, often surrounded by a brightly blazing accretion disk of incredibly fast matter spiraling around the black hole. Hello everyone, welcome back to Zeey. Subscribe to our channel and ring the bell to receive our daily videos. One of the better examples of this in science fiction is the black hole gargantua in the film Interstellar, which was created for the film by physicist Kip Thorne. While this is true for some black holes in the universe, it is not a hard and fast rule for all of them. There are black holes that are merely event horizons without an accretion disk due to a lack of material to eat. But, regardless of their conditions, black holes all have one thing in common. An event horizon is a point beyond which no light or information may escape. This means that the singularity at the black hole center will never be witnessed. Except in one hypothetical case, which, if seen, may drastically change our view of the cosmos. This is accomplished by the use of revolving black holes. Because whatever generated it, such as a star-going supernova, would have been rotating as well, revolving black holes will be the most common sort of black hole in the universe. A Schwarzschild black hole is a hypothetical black hole that is not charged and does not rotate, though it is more of a thought exercise than something that will be experienced in the universe. However, Schwarzschild black holes have some intriguing potential if they might exist or be created. More on that in a later video. While rotating black holes are most likely the rule in the universe, there is a chance that some of them, most likely rare, spin very quickly, such as those created by rapidly rotating stars that go supernova. We know that stars like this exist, and that they revolve at speeds close to those required to kill them, such as the star Regulus A, which rotates at 86% of the speed required to break itself apart, leaving the star in a horribly squished oval shape. If this transfers to quickly spinning black holes that develop during supernovas of these types of stars, we have a very interesting beast on our hands. A stark singularity. These have not yet been observed in nature, and if they do exist, they will be among the strangest phenomena in the cosmos. What happens in a rapidly rotating black hole is that the singularity can form a ring rather than a point. This would result in the formation of two event horizons, and as the spin rises, the event horizons are anticipated to shrink towards the singularity until they eventually match, exposing the singularity to the cosmos. The heart of a black hole is visible to all. There are several unanswered questions here, the most important of which being why we don't see these. It has been proposed that naked singularities are extremely unstable and may not exist for long. That could be a good thing, because encountering such a monster would be disastrous. The immediate vicinity of a naked singularity is fundamentally uncertain. Because of the enormous distortions of space and time near the singularity, the principles of physics, particularly general relativity, fail in this environment. Any star or planet passing into the vicinity of a naked singularity would almost certainly be destroyed in a spectacular fashion. The physics of the matter, however, is a puzzle involving the two rival sets of physics rules applied in this situation, quantum mechanics and general relativity. They make two contradictory predictions in the interior of black holes or near a naked singularity. This disparity is straightforward to cope with in the case of a black hole. Simply consider anything beyond the event horizon to be no longer a part of our universe. This also applies to the singularity thought to have created the Big Bang. You can't see before a particular point in the Big Bang, therefore you don't have to worry about identifying the singularity that caused the universe, if that model is right. However, in the case of naked singularities, you must deal with the disparities because they are no longer veiled. Nobody knows what we would see if we did happen to spot a naked singularity. However, it is hypothesized that naked singularities, like black holes, spin, which may provide a clue as to how to identify naked singularities, if they exist, and distinguish them from black holes, which are clothed singularities. However, it is equally possible that quantum effects regarding naked singularities always clothe them, as in the case of black holes, where the event horizon conveniently hides the singularity, or in the Big Bang, where the early universe's opaqueness before about 300 to 400,000 years after the Big Bang obscures the singularity there. Nature may just not allow us to see singularities and will always find a method to conceal them. This is where things start to become creepy. An event horizon, an opaque early universe, and a shaky invocation of quantum phenomena appear to be three distinct methods of concealing a singularity. That appears fairly contrived in a simulation theory sort of sense, and that it simply appears to be a convenient, if patchy, way to hide things that contradict physical laws. But that's just the way the universe works. But if naked singularities exist and we can freely examine them, the future looks promising. We'd be able to really watch a star collapse to become infinitely dense and investigate some of the conditions of black holes that are concealed to us in typical black holes with event horizons. It could also reveal why general relativity fails under these conditions, providing us with a much more complete picture of how the cosmos operates. Another hypothesis is that black holes simply cannot rotate quickly enough to form a naked singularity for whatever reason. But that seems strange, since there is one known black hole that spins incredibly quickly, but not fast enough to produce the phenomena. Another sort of singularity is much more enigmatic, since it may have consequences for the creation of the universe itself. Physics enjoys contrasts, and they are abundant in nature. Simply reversing the equations describing a black hole produces the opposite outcome, a prediction of a white hole. A white hole is a singularity with mass and gravity that draws you in, yet you can never approach it, and the event horizon of the white hole spews out stuff. A white hole cannot be entered, at least not until it becomes a black hole. However, it would emit light, information, matter, and energy in the opposite direction that a black hole absorbs them all. Despite this, there is a lot of evidence for the existence of black holes, but nothing concrete for white holes. It's unclear why this is happening, but one possibility is that we're seeing them in the form of gamma-ray bursts, which would make sense given that white holes are inherently unstable and collapse on themselves almost immediately due to their own gravity, transforming into black holes. They would appear at random in the cosmos, emit energy for a brief period of time, and then vanish, fitting the characteristics of a gamma-ray burst. And there is a contender for this position. Gamma-ray bursts are classified into two types, long and short, and have been linked to neutron star mergers and supernovae. But there is one outlier. This burst, known as GRB 060614, was identified on June 14, 2006, and because it was a lengthy burst, a concomitant supernova was expected. It never happened. This burst has nothing to do with a supernova, and aspects of the signal suggested that it wasn't a regular gamma-ray burst, but rather a new category in its own right. Following that, Redder and Heller proposed in a study that it could have been an observation of a white hole's brief existence. However, there is one other incident that appears to be a white hole. It's the Big Bang itself, where something happened, an original singularity that may have been shortly before the start of the universe, containing all of the energy and space-time we observe today, that exploded in the expulsion of a massive amount of energy, leading to the formation of matter. It essentially fits the requirements. If it was a white hole, it raises some interesting questions. One theory holds that white holes represent the other side of a black hole. Matter falls into a black hole only to be ejected on the other side. It's unclear where it'll end up, although there are several theories. One theory holds that black holes act as portals to other universes, and that each black hole on the other side represents its own Big Bang, spawning a daughter universe. This might also be said of time. A black hole may exist at one point in time, while its equivalent white hole may exist at another. But if the Big Bang was a white hole, the black hole that birthed it had to be supermassive, but we don't know what the universe it resided in was like. It might not have had an issue with a lot of mass. But once you start thinking about other universes, each with its own set of physics laws, the possibilities for those universes become overwhelming. The Fekan worlds theory, proposed by physicist Lee Smolin, is an intriguing idea. This operates similarly to natural selection in biology, except it applies to universes. So you have a black hole collapsing, which makes a white hole, which creates another universe on the opposite side. Because its fundamental features may differ from those of the original cosmos, many events may occur. These worlds may have varied numbers of their own black holes, or none at all. If there are none, you have a universe that cannot create new universes. It produces fewer universes when there are fewer. However, if it contains a large number of black holes, as our own universe has, it will produce an enormous number of new daughter universes. At that point, it begins to resemble natural selection and evolution. This would imply that successful worlds, if you will, produce more comparable universes with a higher probability of having similar physical rules to the original. The new universe may even be defined by the universe that gave birth to it, much like a kid resembles its parent. In science, you may apply all kinds of familiar terminology to this, but in a totally different, extremely bizarre context, such as reproduction, mutation, natural selection, and so on. This is not to claim that universes are alive, merely that they mimic features of life in certain extremely theoretical ways, but they are ultimately what allow life and intelligence to exist at all. This is when things become interesting. The idea of Fekan universes populating the multiverse with successful offspring universes provides an easy solution to the fine-tuning problem. The trouble with fine-tuning is that a whole set of characteristics have to be just correct, or almost so, for life to develop in our cosmos. Change those parameters even slightly and horrible things happen, and there are a lot of them, and we're not far enough along to know what they all are in order to arrive at us. Some of these parameters are very fundamental, such as changing a number in the Big Bang and causing matter to cease to exist, or changing the laws of physics and causing motion to behave differently, or changing chemistry and preventing complex organic interactions for life to operate on, and so on. You can argue all day about parameters spanning from the Big Bang to the formation of the Earth, claiming that if the laws had been slightly different, the chain would have broken and we would not be here. Nonetheless, it occurred. However, given the Fekan universe hypothesis, it just becomes a logical consequence of how the multiverse operates. A successful universe with many black holes that create other universes like it, and every now and again, possibly even frequently, you will obtain a universe that allows for intelligent life as we know it. Lesser worlds die, or nearly die, and reproduce less, while only branches of successful universes reach the point of reproduction. Interestingly, this hypothesis, which was published in 1992, made several predictions that appeared testable, but it's been contested whether they've held up, and in one case, they may not have. Only time will tell whether this little-known hypothesis is right, and black holes represent new universes, including our own, or if the similarities between the Big Bang and white holes are purely coincidental. Alright guys, this video ends here. Subscribe to our channels for regular, in-depth studies of the fascinating, strange and unknown parts of our beautiful universe. Thanks for watching.